You're never going to believe this. We're going to do yet more classic problems because I'm not just that creative in coming up with these titles. But the point being that in theory, you should be able to do these because there's no more new material in order to cover these. But it brings in some review material that you may have forgotten or you may need some hints on. So that's what that means. These are problems that, you can't really say you took calculus if you didn't do some of these problems. So for example, we have a ladder problem. This is the classic problem where you have a wall or like there's a house. This is the side of a house, let's say. And this is your outside. Hopefully it's concrete because I don't want you putting a ladder up against your house unless there's something really stable there. Okay, so that means there's a 90-degree angle here and you're given usually like the length of the meter. So in this case, I'm just going to make up the length, 10 meters. Okay, I have never seen a 10-meter ladder, but it doesn't matter because this is a pretend math problem. And so try not to get too literal anyway. And so what you do is you'll say like how far away from the wall the foot of the ladder is. So you have to tell someone, let's say it's 2 meters away. Okay? And the other thing is, and this is always this morbid thing that's happening, the ladder is always sliding that direction. So in other words, that same length of ladder is going to end up looking like this, and again, this should not be happening in real life. This is just a math problem. Okay, it's just because we want to set up some kind of type of problem that really matters in real life, but we want to give you a visual of it. And so we tell you what the rate is, let's say like 1 meter per second in that direction. Okay, we've got all that information there. And then we're going to say, if that's happening, how fast is this moving? Now, if you want, you can pause the video and try to do it. Okay, so if you didn't pause the video, that means you want me to show you how to do it, which is fine too. So the first thing you want to know is you want to figure out how you know that side. And you can start by just practicing on the 10 and the 2 if you like. That's fine. Or you can wait until you have this distance, which is currently 2, have that distance as a function of time. So let's just give this thing, first of all, let's figure out how you would do this. If you have a squared plus b squared equals c squared in a right triangle like this, a squared plus b squared equals c squared, then if you're looking for a leg, then it would be c squared minus a squared square root. And you don't have to worry about plus and minus because it's a physical triangle, so the negative doesn't matter. Okay, so in this case it's 100 minus 4, so square root of 96, and we don't really have to simplify that. We're just trying to get our bearings here. So now let's figure out what this leg looks like this leg of the triangle looks like over the course of time. So in that case, let's call it L, length of the leg, is, as a function of time, is going to be 2 plus t, because it's 1 meter per second. If it were 2 meters per second, we would put a multiplier in front of that t, but it's 1 meter per second. There you go. And so what is this height going to be? Well, the 10 is not changing. This is a constant. Okay, so we don't have to have an expression for that guy, but this, I'm going to call this h. H of t must be square root of 100 minus the square of this guy. So what is the square of that? So let's see, if we square that, we get 4 plus 4t plus t squared. All right, that's what happens there. And so we want to actually find what is going on with h. We can't, we're not doing a minimization question, so we can't deal with just the square of the function. We actually want to know the actual rate. So 100 minus 4 is 96. And then minus 4t and minus t squared. Okay, so do realize that eventually t is going to be too high and this isn't going to be meaningful anymore. But that's okay. The question is going to ask you something like, when the ladder is 2 meters away, what is going on? So for example, they could say when the base of the ladder is 3 meters, when the base is 3 meters away from the wall, how fast is the height changing? But usually they're going to use the same setup as the original diagram. So we want to know h prime of 0 is usually what you're looking for. Okay, so let's go ahead and look for that. Another possibility is you could just make this length t, but then you would look for h prime at 2 because it will have already been sliding for 2 seconds. Okay, so you can put that t equals 0 wherever you want, but then that's going to affect where you take the derivative. So it's fine, just keep track of what you're doing. Okay, so we want to take this derivative. So derivative of h with respect to t is going to be 1/2 times the junk inside to the power of -1/2, and then times the derivative of all the stuff inside here. Okay, there's a lot of minuses in there. That's because why? Because, well, the height is dropping, so we expect the derivative to be negative. And I'm just trying to clear off to make more space here. Notice we just ended up with a 1/2, so we can get rid of the 4 and make it a 2 and get rid of that 2. So what we end up with is h prime of t equals, in the numerator, -2 minus t over the square root of all this stuff. And it looks horrible, but it won't look horrible for long because t is equal to 0. So h prime of 0 is going to be -2 over square root of 96. And anyway, this problem is sufficiently different from the one in your worksheet that I don't need to continue this, but at this point you would plug this into a calculator and get some kind of numerical answer, and it's in whatever units the original problem is, meters per second, I think we agreed on. Okay, so that's how you do the classic ladder problem. Okay, the next category of problems is the spheres questions. Sometimes we worry about the surface area of the sphere, sometimes we worry about the volume of the sphere. A question like this, I will give you the formula. So the volume is a function of actually the radius, and it is 4/3 pi r squared, pi r cubed, I'm sorry, pi r cubed, obviously, or it wouldn't be a volume. Okay. So in these kind of questions, it'll either say, we know how fast the volume is changing, tell us how fast the radius is changing, or it will mean we know how fast the radius is changing, tell us how fast the volume is changing, and they'll usually have to give you what the current R is. So you're going to do something like this. You're going to say like dV dr equals 4 pi r squared. And so what you want to think about is these things can be unstacked. Okay, so the 4 pi r squared dr, you can think of this in what's called like a differential. So if you happen to know what the change in the volume is, you know what r is, you just solve for the change, how fast the radius is changing. Or if you know how fast the radius is changing, you solve for how fast the volume is changing. In both cases, you still have to know what r is, unless, of course, we're nasty and we say, well, we know how fast the radius is changing relative to the volume, find out what r is. You can do that too. Then you would go back to this formulation and just think of it that way. Okay, so that's the strategy on that question. Yeah. Okay, and another type of question is the cylinder question, and the harder version of the question I'm not giving you. I'm just giving you the easy version of the question. So if you have a radius and a height, the volume, I think we talked about this, but the volume is a volume question, as this is we're pouring some water into this container. Okay, and so the thing is that the height of the container is given, but you only have to make sure that you're not overflowing the container. As long as you're not overflowing the container, it's actually irrelevant. So it's kind of like a teaser. So what you want to do is the base is pi r squared, and so you're going to use that to figure out, you know, what the current height is if you know the volume. So the volume is pi r squared h, where h, you're thinking of h in terms of the current height of the liquid in the container. Okay, so just be aware of that, and you can take your derivatives and you can set things equal, whatever, but notice r is not changing in this problem because you have a fixed container. So the things that are changing are v and h, and they're changing with respect to each other. And again, since it's a first derivative, we have that special first derivative hack. If I know dv dh is equal to some number, then it's dh dv is going to be 1 over that number, in case that hack helps you. So it's all part of the same discussion, so you don't have to take the derivative a second time if you want to find the other derivative. Let me just see if that's all you need. Hold on. Oh yes, there's a nasty version of this problem, and it's a lot of fun, but I'm asking you to think about it, but I'm not asking you anything on the quiz about it. So in this case, you're filling up the same container, but it's sideways, and now the height is going to change differently. It's not going to be a uniform change in height because you're letting the water fill up, and this shape of the size of the thing you're filling keeps changing. So we're not going to do that problem unless you really want me to, in which case come to office hours. But that's a think about problem, and it's not the one I expect you to solve. But this one is fair game, and I do expect you to be able to handle that. Okay, now one of the next problems on your worksheet has to do with angle of repose, although we don't talk about it that way, but it's actually quite fascinating, and I encourage you to read up a little bit on it. The different materials can be poured into cone shapes, and they actually form a natural angle. And 45 degrees is not the angle for dry sand, but if you can see, wet sand does form a 45-degree pile. So we can conclude that the sand that we're working on in this exercise is actually wet. Or haha, we just picked a convenient angle so that we could do an easier problem, which is really more likely to be true. So you can just draw this picture for yourself and imagine that this is some kind of cone, and what we have here, this is a really disgusting picture. Let me try to improve the picture a little bit. Okay, this is slightly better, I guess. So whatever your height is going to be reflected by the height of the whole pile, and radius is the radius of that circle. Okay, and so we're making the claim here in our exercise that this is a 45-degree angle at the top of our pile. So because this is, a right triangle inside, there's a 45-degree angle in here, which is really convenient because why? Because it means our height is equal to our radius, and we can use that trick. And that's my clue for you. That will make the problem a lot easier once you get that, okay? So you're going to simplify your expression, and then you're going to have to calculate things like dv dh, or if you prefer dv dr, but h is r. So you can either think of it in terms of radius or height, it doesn't matter. But you're going to have to take that derivative, and you're going to know when the pile currently has a certain volume. So you need to know the volume, which it is told to you in the problem, is a function of height or now radius. You take your pick. But it says the pile is currently 100 cubic meters, so this is 100 cubic meters, so you solve for like h or r if you've made it in terms of r. So you solve for h. Now you know h, and now you go back and you do all this stuff and you plug in your h over there. Okay, so that's the overall structure of how you do it. And I think in the online quiz I ask you to possibly convert it to centimeters, because the meters is 0.0 something. That's a clue. And then I'm going to ask you to convert that to meters. And then there's some other questions. Okay, so that's your clue for that one. The other question that's on the worksheet, I just want to give you a linguistic warning. It asks you about the period of a pendulum, and it gives it, is given. Okay, so it's given. So don't try to do like what we did before when we said, you know, sine of blah, 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 and we had to find the period. No, you're not looking for the period. That's the wrong problem. So this is a different problem that has the word period in it, but the thing is the formula for the period is given. So don't overanalyze it. It's just a warning. So if you don't overanalyze it, it's actually a really, really easy problem. And if you're having trouble, just ask me. But mostly I think if you're struggling, it's because you're overthinking it. Just pretend like it's a different word that you've never heard of before. So just take the derivative of the thing that's listed and do what it tells you to do. And I think that's just the biggest hint on that one. Okay, and so those are the hints you need for the homework, or for the worksheet rather. And we'll see you in class.